In this video, we're going to talk about the Argand plane. I think that's how you say it. I've been known to mispronounce it. And how that's related to complex numbers and how it's related to vectors. Okay, so there's a reason that IB puts this kind of in the middle of the vector chapters. So what happens is, say you have the complex number 3 plus 4i. What we'll do is we'll graph that using a vector where the x-axis is now the real axis and the y-axis is now the imaginary axis. And so what we have here is we're going 1, 2, 3 in the, here I'll show you. We're going to go 1, 2, 3 in the real direction, and then we're going to go 1, 2, 3, 4 in the complex direction. And so this right here, this point would be the point 3 plus 4i. And so there are lots of, then we can use our lovely little 3, 4, well, then this becomes a 5 in our triangle. So this allows us to put that complex number on a plane, in such a way that that we can kind of see what's happening. And so now when we talk about, let's say that was z was equal to 3 plus 4i. There's a few things they're going to talk about. They're going to ask us to find the modulus of z, and that is how far are you from the origin? Well, we just saw that this is a 3, 4, 5 triangle, so the modulus of z ends up being 5. And we'll talk a little bit more about how to kind of systematically do that, but maybe you see already. If you say we wanted to find the conjugate of z, well, that would be 3 minus 4i, which would mean that we're still moving in the positive, we're moving positively on the real axis, and now we're moving negatively, 1, 2, 3, 4, on the imaginary axis. And so this point that we have here, the initial point, its conjugate is a reflection over the real axis. So if you notice, this point here got reflected over the real axis and moved down here. So we can think about these complex numbers in a similar way that we thought about vectors. So if we had, say we've got that z is equal to 2 minus I, and we've got that w is equal to, I don't know, negative 3 plus 2i. Then what we can do, if we want to add these together, we could do this graphically, or we could, add the real parts and add the imaginary parts. But let's just say, okay, so say I'm graphing z in red, and we went 2 along the real axis, and then 1 down. Here, this first part is the imaginary number z, and then the next one we're going to go in a negative direction, a negative real direction, and then up 2. So we turn around and come to this. We went back 3, 1, 2, 3, and then up 1, 2. And so this was our W. So when we put them together, this may not have been the best example, but we end up having this going from here to here, and that point was at a negative 1 and a positive, a negative 1 in the real direction, a positive 1 in the imaginary direction, so that's just negative 1 plus I. And if you notice, combining like terms over here, 2 minus 3 is negative 1, negative 1 plus, negative 1i plus 2i is a positive 1i. So we can relate this all back to everything we know about vectors. Same idea if you were multiplying by a scalar. Let's say we wanted 3z. Well, then I could just do z, 1, 2, oh, I ran out of space. Okay, 3, something like that, and that kind of gives me an idea of, well, that point becomes 6, and then negative 3. So 6 minus 3i would be what you would get when you have 3 times z, which it's not super profound, but this is the foundation that lets us do some pretty cool stuff.